Alright, so last time we found that there's a very special case of matrix equations where we've got the matrix A times the vector, and that's going to equal some number, lambda, times the value x. And what we want to do is we want to rearrange this into a form in which we can solve for the eigenvalues and the eigenvectors. So often what we'll get is we'll just get A and we'll have to find lambda and v or x, which is the eigenvector, and this here is the eigenvalue. And so let's rearrange this equation. So if I add let's subtract ax from both sides, so that's ax minus ax is equal to lambda x minus ax. That cancels out, that gives us 0 is equal to lambda x minus ax. Because this is a vector, we can take it outside, so we can go x lambda minus a. Now something else that we want to do is we want this here to be a matrix, because if it's a matrix then it makes it very easy for us to solve this equation. And so so we times this by the identity matrix, and that basically doesn't change it at all, but it just makes it easier for us to subtract these, because these now are both matrices. Now, as we learnt earlier, if you have two lines, for example, here, let's put a x and y axis in here. So these are the two lines. What we want to find out is the point in which these two lines intersect. Usually what we do is we go ax is equal to b, and we try to work out where those two lines intercept. But actually what we're doing when we're trying to find the eigenvalues and the eigenvectors is we're actually trying to look along the directions in which the matrix doesn't have a solution, so to say. So it's basically the orientation of the matrix and the importance of the different vectors that are involved. So I'll expand on this a little bit later, but for now we're trying to look for vectors along the lines, so to say. And so that means that there will not be any intersections if we're trying to look along the line. That means that we won't be able to invert the matrix. So A cannot go to A inverse. And that means that the determinant of A is equal to 0. And it's a little bit more difficult to prove it, but for now that kind of gives you some understanding. So what we do is we say that this matrix inside of here is not going to be invertible, and so the identity times the eigenvalue minus the matrix, the determinant of that is going to equal 0. And so we know how to calculate the determinant, we know how to subtract matrices from each other. It's just basically the same way you add matrices, except you subtract each value. And we can solve for the eigenvalue. So let's consider an example where A is equal to 1, 3, 4, 2. And what we're trying to work out for this matrix is what its eigenvalues are, so it's what its lambda is, and what its eigenvectors are. And so basically that's our x, or also our v. So what we're going to do is we're going to put it into the form that we've just derived. We're going to have the identity, which is going to be a 2 by 2 matrix. That's going to times by lambda, and that's going to be subtracted by 1, 3, 4, 2. and we're trying to find the determinant of this is equal to 0. So let's multiply that out. So we've got lambda 0, 0 lambda minus 1, 3, 4, 2, and the determinant of that is equal to 0. Alright, so let's subtract these two matrices from each other. So we've got lambda minus 1, and we don't know lambda at the moment, so we'll just kind of leave that out for the moment. So it's lambda minus 1, that's the first entry. The second entry is 0 minus 3, so that becomes minus 3. We're going to have 0 minus 4, so that's going to become negative 4. And we're going to have lambda minus 2. Oh, sorry. Lambda minus 2. And we know that the determinant of this is going to equal 0. So quite simply, we can just work out the determinant of this 2 by 2 matrix, which we know is going to be A times D minus B times C. And so it's going to be lambda minus 1 times lambda minus 2. And we're going to subtract that from negative 3 times negative 4. And that's all equal to 0. So that's going to be so negative times a negative is going to be a positive, so it's going to be minus 12. And that's going to equal 0. So let me just copy that and we'll start on a new page. Oh. Alright, I'll just do it from memory. Lambda minus 1, lambda minus 2 is minus 12 is equal to 0. Okay, so let's expand this out. Lambda squared minus 2 lambda minus lambda plus 2. Minus 12 is equal to 0. Lambda squared minus 3 lambda. So we've got negative 12 plus 2 is going to be negative 10. Alright, so now we have to solve the quadratic. So we could put it into the quadratic formula, which would take us some time, or we can try and find two numbers that will add to give us negative 3 and will multiply to give us negative 10. So let's think of those two numbers. So one has to be positive and the other has to be negative, because we end up with a negative number here, and two negative numbers would give us a positive number, and two positive numbers would also give us a positive number here. So this negative sign tells us that we have to have one positive and one negative. So two numbers that would multiply to give 10 are 2 and 5, and so if we have positive 2 and then we subtract 5 off of that, you get negative 3. Then we put our lambdas in. And so when this is going to be equal to 0 is if lambda is equal to 5, it will be 5 minus 5. This part will be 0, and so whatever's over here will also be 0. So the first solution is 5, and if lambda is negative 2, then this side will be 0, and it doesn't matter what's on the other side, and so lambda is also going to be equal to negative 2. Alright, so that's the first thing. Now we have to work out along which directions do those vectors act. So basically the way we do that is we use the same matrix, the same form that we had before. This is called the secular determinant, because it's kind of like the singular determinant, secular. So what we do here is we just put in the lambda value that we've gotten down here, and we try and find out what our vectors will be. Okay, or our x dash. So let's make up the matrix. It's going to be 5, 5. This is for the lambda is equal to 5. And let's subtract that from our A, which is 1, 3, 4, 2. Alright, so that is 5 minus 1, which is equal to 4. 0 minus 3 minus 4 and 3. Cool. So that's our first value. Alright, so we know that actually, well, it's probably easier if we just use the form is equal to 0. Okay, so what we've got here is this matrix here is 4, -3, -4, 3, and times by a vector, and let's just say that that's x, y, and that's going to equal 0. So let's see what we've got here. We've got 4x, we're matrix multiplying it out, 3y is equal to 0, and we've got this row here, chuck it down into the column, and we've got -4x, and we've got plus 3y. Now we can arrange this, so 4x is equal to 3y, and -4x is equal to -3y. And so we see that if we divide both sides by 4, we get x is equal to 3 over 4y. And the same is true down here, which is good. That means that we've done it correctly. And so what this is saying is along the line, well, I mean, if we rearrange this, along the line of y is equal to 4 over 3x, along that line, then there's actually no solution. So that represents for us one of the lines. Okay? So along the vector, that basically has